ahead and talk about these patterns now. So, in general, regarding with the quadratic patterns, let's talk about this. So, really, which patterns can we use to factor this following expression? So, notice, I always take a look at the positives. So, really, we have this is two different identities. You have the square identities, the certain equations like when plus times plus equal plus of the same expression versus negative times negative. That, or you can have a positive times a negative. That's the second identity. In this case, what we're seeing here, well, we're seeing it as a positive symbol here and a positive symbol here. This is going to give us a negative, so this wouldn't work out. B wouldn't work out. For this one over here, since this is going to give us positive and a positive, this would basically give us positive. So positive square would give us positive in this case. So this is a possibility, so I would say A would work in that case. Just take a look at the symbols and go from there. And in this case, we're seeing here that x to the fourth, that's perfect square. 3, that's a perfect square as well. X to the 8th, that could be x1 and x4. Y squared could be y times y. This can also work with the coefficients. So there's many ways you can do this. In this case, I think A would work. Try to factor this one as well. So we can see here to factor this, well, 36x4, that can be written as 6x squared minus that by y plus 3. But since this is repeating again per se, this is a parentheses by the way. We're doing this by we're gonna multiply this by 6x squared plus that by y plus 3. So this is a negative times the symbol here is negative in this case. So we're seeing here that this is the only one. Option B would make sense in this case. Because negative times a positive would give us a negative. Always take a look at the symbols. The symbols give you a real good indicator of where certain things are. To factor polynomials with structures, so always consider really what are the u and v values for certain things, and then factor the expression after. That's kind of really how you would see it. So identify which expression you want to use first, whether it's a negative positive identity, or it's going to be a negative negative identity, or a positive positive identity. So factor the expression. So let's try to factor this equation first. So in general, over here. In general over here, we can try this over here. So we can see that we have a 25x squared and a 9. So the v value is going to be a 3. But we're seeing that there's a negative symbol here as well. So that means that there's going to be a negative times a negative situation. The b, this is the... So a good way to kind of put this is the a value, b value, and c value. We're seeing here this is the negative value over here, but we're seeing here that this is also being multiplied to get a positive constant. So there's definitely going to be a negative scenario in this case. So let's try to put this in there. So we have negative 3, and we also have another negative 3 in this case. This 25x squared can be written as 5x squared, so you can do 5x squared. You can square that. So you can write that as 5x squared. 5x squared. Excuse the background. Yeah. So yeah, and then after, as you can see here that this is negative 15x squared minus 15x squared, which you distribute, you're going to get negative 30x squared afterwards. This is kind of how you would factor the first one. Again, always identify first which expression you want to factor, what is the u and v value you want to use, and then use that to your advantage to find what kind of expression would I want. Negative square expression, a positive square expression, or a negative positive square. Negative positive expression. Expression. What I mean by expression, I mean identity in that case. Let's try to factor this one here. The x and y value in general over here, we're seeing that the square of x can just be written as x. And the negative 49 y squared, the central here is we're seeing here is there's two exponents here. There's a negative value here. So you can do x minus 7y, and then you can do x plus 7y. Because our central symbol that we're using here in this case is going to be negative, we're going to have a negative times a positive. We're going to have a negative times a positive. Bear with me 1 second here. Oops. Give me 1 second. Okay, so yeah, this is kind of really what we're seeing here as a result because of this guy over here. This thing over here. The negative symbol over here is kind of what's getting it away. Let's do an example problem. Let's do a simple example problem over here. We can factor the expression here of, what is the u and v guys? So we can factor the expression as u plus v squared, where u and v are either constant integers or this. What is the u and v value? So notice that we're seeing here is that there's an x plus 3 term here that's similar in both of these, and we have a 49 here as well. So you can obviously do here is you can do you can do x plus 3 plus that by times that by x plus 14 plus that by 7 in that case. But I wouldn't do that because we're seeing that x plus 3 is a commonality here. So definitely x plus 3 plays a big factor in this. V cannot be 7, 14, or 49. So let's just do an option of elimination. I think that's better. Because we have a 49 here and a 14, we're seeing here that this is going to give us a 7. V is definitely going to equal to 7 because 7 plus 7 is 14, and 7 times 7 is 49. We're not going to see anything here regarding with V being anything above 7. So this option's out, this option's out, this option's out, this option's out. It's either between A or B in this case. Now, could it be x plus 3 per se? Maybe. Actually, yeah, this is going to work in that case because the reason why is simple, is that because we're seeing it at the least common the least common number that we can do here for both of these factors, which is x plus 3. So therefore, that's why it would be A in that case. So you can do process of elimination to find really your answer what you want in that case. That's kind of really how you would do it in that case. Here's another polynomial identities equation. Elena was asked whether this equation is an identity. She performed the following steps for this. Can you state that the equation is a true identity? If not, which did she make a mistake on? Let's take a look at the steps first of really what she did here. Pause the video if you guys want. You guys can always do so. So really what we're seeing here is, let me get my red marker out actually. So really what we're seeing here is that she performed this, right? We get it. She performed it. Yeah. So let's see here. So she first distributed first. That's good. Okay, so I see what she did wrong here. The very first step, when you factor this out, the second part, negative x plus 1 squared. Yes, this is actually correct. The fact that she did here is that x squared plus 2x plus 1, that's fine. But you need to distribute the negative sign because that's kind of where we're getting at here. You have to distribute the negative sign because that's also included in the equation. If you didn't do that, that's kind of a problem in that case. So distributing that kind of is what's kind of happening here. And I think that's kind of where the issue went here, because we can see here that you're adding everything right. Yeah, she's doing that correctly. The only problem is that she forgot to distribute this negative sign. You have to distribute the negative sign on the other side of the expression on the other expression to make sure they have a complete equation afterwards. That's kind of where we're seeing here. So she made a mistake in step 1 for sure, because you have to distribute the negative as well, because that's part of the other expression. Now let's do some of the example problems over here. Which of the equations are true identities? So we can do a simple here. So let's see here. So is this a true identity? No, this is not a true identity in this case because we're seeing here that negative 8 times positive 8. I just look straight directly at the constants. Negative 8 times positive 8 is negative 64, not positive 64. So this doesn't work. This one over here, let's see. You can always check each equation first and see if it works. So 3m times 6m, that's 18m squared. That's good. So we're seeing here that's good. 12n minus 12mn, that's because you're seeing here positive 12m times n, negative 12 times m times n, that's 0. And 2n times negative 4n, that's going to give us a negative 8n squared. So this works in that case. Equation A is not true. It should be positive 64. Equation B is true. B is a true identity. Now let's go over the final thing. It's called geometric series. So let's talk about geometric series, what it is, and go into that depth as well. So money in a bank account. Money in a bank account. Let me just double check how far we're at, just to make sure where we're at. And if you guys have any questions, please feel free to let us know in the comments as well. So let's go over now in terms of geometric series. So let's talk about year beginning and a money in account. So let's say you got like $5, let's say, for example. You got like $5 in your account, right? So you got $5. That's going to give me $5. Let's say it exponentially increase. What's that going to be? Second year, what's going to be? It's going to be $25, right? So it's going to become $25. And then number exponentially squares that again. So that's going to be 625. And then you do 625 625. That's going to give you another number. So you're going to basically square this until the Millennium Falcon goes into the abyss, basically. So you're seeing here that the money in the account is going to exponentially grow at a certain point. That's kind of what we're seeing in the geometry series. At a certain sequence, it's going to exponentially multiply to its capacity. That's kind of what we're seeing here. So let's talk about finite and infinite geometric series beforehand. Finite geometric sequences, there are listed numbers with an ending because it's finite that progresses by multiplying or dividing each term by a common ratio. Divide each number in the sequence from the number before it to get to the common ratio. So for example, let's say you have 2, 6, 18, 54, and 162. The common geometric sequence that we're seeing here is as being multiplied by 3 every single time. So the common ratio here for this one is going to be 3. You're multiplying by 3 each time. So this is going to give me 3. Yay! 1, 2, 4, 8, and 16 over here. You're seeing that this is multiplying by 2 each time. This is another geometric series because we're seeing it's multiplying by 2 each time. This is multiplying. Anything that's multiplying by common ratio or dividing, that is a finite geometric sequence. So, in general, that's there. Let's say we're doing 20, 10, 5, 2.5, 1.25. That's dividing by 2 each time as a sequence in that case. That's a common ratio dividing by 2 in that case. To note as well for finite geometric series as well, the sum of the terms of a finite geometric sequence has a limited number of terms. Let's say you have 2 plus 6 plus 18 plus 54 plus 162. The sum of terms of a finite geometric sequence, there's a way you can do this. There's a formula for it. It's S subscript of n is equal to a times 1 minus r to the n divided by 1 minus r. So this is kind of how you kind of calculate for finite geometric sequences. It's a much more easier way to do it where n is represented as the number of terms, a is equal to the first term, r is equal to the common ratio. I don't want to do all the multiplication for multiplying to find 3 and all this nonsense. Because, 2 times 3, 18, 54, that there's a lot of ways to do it. This is a very, very good shortcut to find, how to find the sum of the terms of a finite geometric series. I don't want to do the whole math, like figuring it out, etc. So this is kind of the way you could do it. This is the proper way of doing it. So how does that work in our equation in this case? If let's say you want to find the addition for all of this, since you want to add all this, right? S subscript of 5 is going to be equal to 2, which is the first term, multiplied by 1 minus that by the common ratio, which is 3, raise that to the fifth term, divide that by 1 minus that by the common ratio is 3. So you're going to get essentially how to do all that math, you're going to get 242. That's the finite geometric series. Just apply the formula, put that in the thing, you're going to get your answer. If you want to do a whole proof of that formula, there's a whole calculus AB method they do with this for proof of the formula. Here's a way to do it for Calc 1 here, guys. So this beautiful, majestic equation for proof, so if you guys are interested, S subscript n is equal to AR0 plus this. You're seeing that? You can multiply the R common ratio on the left side. You can subtract that from the total sum of that. And then afterwards, you can see that after you do all that math, for any R that's not equal to 1, you can get that. So that's the proof of the formula if you're interested. Let's do a geometric series word problem. Yes, let's do one of these bad babies. So Rosie went on a hiking trip. The first day she walked 18 kilometers. Each day since she walked 90% of what she walked the day before. What is the total distance Rosie traveled by the end of the 10th day? So we want to round this answer to the final nearest kilometer. Yay, let's do it. So we got, what's this big mama equation here? Put this beautiful equation in. So the first day she walked 18, cool, she walked 18, yay. 1 minus that by 90% of what she walked the day before. This is essentially equal to 0.9x. So this is going to give me 0.9x. This is literally the common ratio. This is basically 90% of what she walked the day before. It's literally just 90%. So this is going to give me 0.9. Raise that by the 10th power, because that's the number of terms. Divide this by 1 minus 0.9. And then you get your answer from that. Alright, so that's kind of really what we're seeing here. You guys can pause the video if you guys want. And you guys can take a look at it. So this is kind of what we're seeing here. S subscript is 10. If you put all this in, you're going to get approximately 117.24 kilometers or 117 kilometers. here's some practice time, guys, for you guys. Pause the video. You guys can. I'm not gonna solve these for you guys. These are challenge problems. I'll probably put a little bit of a little answer key maybe here in the shorts. You guys can take a look at that for the practice time. Here's the first challenge problem.
Oh, you have to hide, bro? Oh, hell no.
Actually, you know what? While we're at it, let's just try solving these. So, let's try to do this. So, let's try doing this problem here. So, 4x squared plus this positive 8. You guys can do this as well. Yeah. So, here's the first one. Let's solve the first one. Here's the second problem. And here's the third problem. You guys can stay tuned in the next video. We're going to be going over these problems by itself. Alright, but anyways, guys, thank you guys so much for watching this video. And I hope you guys have a